Hello, bachcho, and welcome. Today, we are going to look at a really beautiful and important topic from our first unit on electric charges and fields, Gauss's law. Now, I know the name sounds a bit heavy, doesn't it? But trust me, the idea behind it is so simple and so powerful. Let's make sure we understand it perfectly, in a way that is completely exam safe.
Okay, so before we jump into any formulas or definitions, let's start with a little puzzle, a little mystery. Imagine you have a hollow metal ball, okay, a sphere, and you put a whole lot of electric charge on its surface. Now here's the question. What do you think the electric field would be inside that empty space in the ball? Common sense might tell you, well, there's charge all around, so there must be a field inside. But something truly amazing happened.
You know what? The electric field inside is always, and I mean always, zero. It's completely shielded. Now, this isn't just some random fact for your textbook. It's the actual principle behind something called a Faraday cage, which is used to protect very sensitive electronic equipment from stray electric fields. So, how on earth is this possible? Well, Gauss's law gives us the most beautiful and elegant answer. Let's build up to it step by step.
To really understand Gauss's law, I want you to forget about physics for just a moment. Forget charges, forget fields, forget everything. We're going to use a very simple, everyday idea, an analogy involving water and a net. I promise you, if you get this, you'll get the whole concept.
So imagine there's a tiny little spring at the bottom of a swimming pool. And this spring is constantly pushing water outwards, in all directions. Up, down, sideways, everywhere. Now in our world of physics, a positive charge behaves exactly like this spring. It creates an electric field that radiates outwards, just like that flow of water. Simple enough, right?
All right, now let's imagine we take a small net, shaped like a sphere, and we put it around our little water spring. Naturally, this net is going to catch all the water that's flowing out through its surface. Now, this total amount of water passing through the net, we give it a special name. We call it flux. And in our physics topic, this is what we call electric flux. It's just a measure of the total electric field passing through a closed surface. And now, here comes the most interesting part. What if we take away our small spherical net and replace it with a big cube-shaped one? Do you think it's going to catch more water? The answer is no. Think about it. The spring inside is still the same, right? It's still pumping out the same amount of water every second. So the total flow, the total flux passing through this new net is exactly the same. And this is the main idea. The total flux only depends on the strength of the spring inside the net. It doesn't care about the net's shape or its size. Please remember this.
Okay, now that we have this simple water and net picture in our heads, we are ready for the official part. The definition you need to write in your exams. Let's look at the formal statement straight from your NCERT textbook. So Gauss's law states that the total electric flux through any closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface. And the formula looks like this. Now, I know it might look a little intimidating, but I promise you it's just saying exactly what our water analogy just showed us.
Let's just break it down, okay? That scary-looking integral symbol on the left, that is just the total electric flux. In our simple idea, what was that? It was just counting all the water passing through the net. Simple. On the right, we have Q enclosed. That's the enclosed charge, which is nothing but our water spring that's sitting inside the net. And that epsilon naught, epsilon zero, that's just a constant of nature. You just use its value in calculations. There's absolutely nothing to worry about. See? The formula is just a grown-up, formal way of writing down our simple idea.
Okay, so the law is beautiful, but so what? What is its use? Why do we even need it if we already have Coulomb's law, right? Well, the real power of Gauss's law is that it becomes a brilliant, brilliant shortcut for finding the electric field, but only in special cases where things are arranged symmetrically.
It's like a 4-step magic trick. First, you look at how the charge is arranged. Is it a sphere, a long straight wire, a flat sheet? Second, you choose a smart net, what we call a Gaussian surface, that perfectly matches the symmetry. So for a sphere of charge, you use a spherical net. For a line of charge, you use a cylindrical net. Third, because you made such a clever choice, all that complicated math just simplifies to E multiplied by area. And finally, with that simple equation, you can very, very easily find the electric field, E. It's fantastic. So let's go back and solve our starting mystery. We had that hollow charged sphere, remember? Let's use our shortcut. We'll draw our net, our Gaussian surface, inside the conductor. Now ask yourself the most important question. How much charge is inside our imaginary net? Well, since all the charge is on the outer surface, the charge enclosed, Q enclosed, is 0. And if Q enclosed is 0, what does Gauss's law say? The total flux must be 0. And for that to happen, the electric field, E, has to be 0. And there you have it. The mystery is solved. It's that elegant.
Chalo, now for a very, very important section, especially for your exams. Let's talk about some common mistakes, some silent killers that can make you lose marks without you even realizing it. So please pay close attention.
The first big mistake is that many students think Gauss's law only works for nice symmetric shapes like spheres. This is absolutely wrong. Gauss's law is universal. It is true for any closed surface and any arrangement of charges. However, it's only useful for us to easily calculate the E field when we have that symmetry. So just remember this one line. Gauss's law is universal, but its easy application requires symmetry.
Here's the second trap. What about a charge that's sitting outside our Gaussian surface? Does it have any effect? Many students think it has no effect at all. Well, that's not quite right. The outside charge definitely creates an electric field at the surface. But for a closed surface, any field line from that charge that enters the net on one side must also exit it on the other side, so its net contribution to the total flux is 0. Just think of it like this. What goes in must come out. The law only really cares about the net charge that's trapped inside.
And the third mistake. This one is very intuitive, so be careful. If I draw a bigger net, a bigger Gaussian surface, it feels like it should catch more flux, right? Wrong! Let's go back to our water analogy. Does the spring care how big your net is? No, the flux only depends on the charge inside. When you make the surface bigger, you are moving farther away, so the field becomes weaker. This decrease in field strength perfectly, mathematically, cancels out the increase in the area, so the total flux stays exactly the same.
So let's just quickly pull everything together, summarize what we've learned, and see how this amazing idea fits into the bigger picture of physics.
Okay, here are the absolute key takeaways for your exams. Point number 1. The core idea is simple. Total flux depends only on the charge enclosed inside. That's it. 2. The formula you must remember is this integral of E.dA equals Q enclosed over epsilon naught. 3. Its key use is as a powerful shortcut for symmetric problems. And 4. For static charges, it's just another, more elegant and general way of saying what Coulomb's law says.
And finally, why is this law so incredibly important? I want you to appreciate this. Gauss's law isn't just some random topic in your first chapter. It is one of the 4 fundamental Maxwell's equations. And these 4 equations, well, they're the foundation of everything we know about electricity, magnetism, and even light itself. Every single motor, every circuit, every mobile phone in the world works because this law is true. So when you understand this, you're not just learning for an exam, you are understanding a true pillar of modern physics.